the solution to quiz 10 unless one of you would like to put up your solution. Again, you have today's 2 quizzes for possible extra credit if you share your quizzes. And also I'm giving you 2 quizzes that will be due on Wednesday, and then that's the end of the quizzes. That's the end of the opportunities for extra credit. Would anybody like to put up their solution for nuclear material science? Okay, Alicia, you'd like to do that? Okay. Let me make you a... Okay. Okay, I can see that. Okay. That's a good idea. Thanks, Russ. Well, okay. Yep. Yep. you definitely had the right approach on that. Okay. Did anybody have any questions of Alicia before I put that off? I've sort of put my solution up on the board while she was doing hers. Does anybody have any quick questions for her? Okay, Alicia, thank you. I'll put you back with the group now. Okay. And what I've done in the meantime is I've sketched our original cross section. Actually, I should have labeled here. The neutral axis 6.04. This is our baseline. If I go back to a force and stress free body diagram, I have tension on the bottom, compression on top. I have my 10,000 newtons acting up here, 10,000 newtons acting down there because the sum of forces in the y direction that equals 0. I have my stresses here, which are going in that direction because of the loading. I then cut it right here, and I looked at the upper half. I've sketched the upper half here. Again, I draw the free body diagram of this upper section, so I still have my 10,000, 10,000. And then wherever the cut hits here, I'm just putting the plane stress that's above that. Hopefully you can, when you look at this, you know that there has to be a horizontal shear acting in the cut to make the system be in equilibrium. This force and this force make the thing want to rotate counterclockwise. So if this stress is acting in this direction, it sort of makes it want to go that direction. So you need the horizontal shear force to be going in this direction to make that an effective clockwise moment to put this in equilibrium. We know that this horizontal shear has to be FQX divided by I. My force is this force. My X is the length of this, which was 8 meters. The I was the rectangular moment of inertia for the entire section, which we had from before, which was 1368.7 times 10 to the minus 8 meters to the fourth. And what I've tried to do on these quizzes is I've tried to use one shape so you won't have to continually do different neutral axes, rectangular moment of inertia. You can just carry that forward. So we needed to find out what Q was. Q is area times the height from the neutral axis to that centroid. The area of the triangle was 1/2 the height times the base, which is 6 times 4. Y is the distance from the neutral axis, which is 6.04 to the centroid of that shape. So it took you 11 to get to that, 11 to get from here to here, and then 3/4 was that distance. That made this hole, when I multiplied it out, 100.7. I'm 10 to the minus 6 meters to the third. If I threw that back in here, I came up with a value of 5,888.4 newtons. And I put a minus here just because it's going in that direction. Any questions on that?
I have a question.
Yep.
How do you conclude which direction the shear is going?
Okay. When I look at this force and this force acting on the member, this force acting up, this force acting down, it makes it want to rotate counterclockwise around the z-axis. If I then look at the plane stress that is generated by the moment that is created, it's going in this direction. So here, if this is going in this direction, we need something to make this want to rotate clockwise in order to counterbalance this counterclockwise. So we know there's a shear here. We're going to find out the magnitude, but to find the direction, just look at the way this is going. It has to be going in this direction to make it be an effective clockwise moment to balance out that counterclockwise moment. That answer the question, Chris?
Yes, thank you.
Or do you understand what I said? I'll ask that both ways.
Yes to both.
Okay, thank you. Okay, if we go back up and do a look now at the lower half. So I'm going to erase this. And now I have the lower half. I still have this force acting up, this force acting down, but now from where I've cut it, what I've done is I've just cut it here, and now I've looked at the stresses that are over here. So I have a little bit up here that's acting in that direction. The majority of it is down here acting in this direction, because again, I've just cut it here and taken this down. So again, this and this make it want to go counterclockwise. So I need something to make it want to go clockwise. So we know we're going to have an H in the cut. And look at this to make it go clockwise. This has to be going in this direction, so that this plus this tend to make it want to go clockwise. We're then going to use this exact same equation again, because no matter how you calculate H, it always has to be equal to this. So if I go back and look at this value is the same, that value is the same, that value is the same. So we need to find a new Q. Q is still A times Y bar, but we know because of equilibrium that this H going in this direction had to equal the other H going in the other direction due to equilibrium. So we know that this Q had to equal the Q from the new calculation. And for the new calculation, since the cut was here, this area is going to be everything that is below that cut. And that area was a rectangle, which is 6 times 2, times a semicircle, which is 1/2 pi r, which is 5 squared. Okay. Then we need its centroid, and the centroid is the centroid of this shape here. So we have to do a little new neutral axis for just the area of interest. The nice thing is we still have our baseline. So this is going to be the sum of the areas times y bars divided by the sum of areas. So for the semicircle, it's 1/2 pi times r, which is 5 squared. The y bar is, from what we did earlier, 5 minus 4 times 5 over 3 pi, plus this other area, which is 2 times 6, times this centroid, which is 5 plus half of 6 is 3, so that's 8, divided by the areas. And so when I took this algebra, substituted it into here, took this algebra, substituted it into here, lo and behold, I got exactly the same thing that I did before to substitute back in here. So I ended up with, again, 5,888.4 newtons. And again, since it's going in that direction, it's going to be plus this value and this value When you put the lower and upper half together, this one going in that direction, the other one going in that direction, cancel one another out, so you know it's in equilibrium. So these two have the same magnitude, but they have a different direction because, again, it is a vector. And it was sort of, you knew what the answer had to be because you couldn't have a different h in this direction and a different h in that direction for equilibrium. I haven't looked at any of your solutions yet, and I realize you might have slightly different depending upon how you round it off, but you still should have pretty much the same answer. I think somebody was asking me a question and then the little bubble disappeared. So does anybody have any questions on this?
So we're essentially using the lower half to verify our calculations to make sure that we are in equilibrium?
Yes.
Okay.
And then the other thing is I wanted to demonstrate to you that whenever you have a problem to solve, and in this case, we cut it right here, and I asked you to find essentially what the horizontal shear was. What I wanted to show you is when you have an opportunity to do this, when you have the cut here, you can look at the upper half and calculate an H, or you can look at the lower half and calculate an H, and you know wherever you cut these, they have an upper half and a lower half, that those values must be equal and opposite because of equilibrium. So when you're solving the problem, you have, hopefully from this quiz, you realize there are two ways you can do it. You can isolate the upper half, do all that math, or you can isolate the lower half, do all that math. You're still going to come out with the same answer, but hopefully you'll realize, it's a lot easier to do this upper half to come up with an answer than it is to do the lower half. But again, you're still going to come up with the same answer.
So in a problem, if we were just given a problem and asked to come up with H, we would just figure out which one was simpler and find H and just assume that the H value was the same for the lower half.
Yes. If you had time, you might want to go back and check it. Let's look at this and let's cut this at a slightly different place. Any more questions on this before I erase it? Okay. I'm going to erase all of this. I'm going to go back to this free body diagram. Okay. And let's say I cut it let's say I cut it at let's say I cut it 9 centimeters from the baseline. So I cut it right here, and I ask you to find in that cut what is the horizontal shear. You have two ways you can do that. If I come back up here, I still have my neutral axis. This time I know the cut is slightly above that. So it's going to go here. So I can look at this as either, if I cut it here, and I'm just going to look at what I have. Actually, I should make that the wavy line. Okay, this is where I made the cut. So when I go to draw my free body diagram to either look at the upper half or the lower half, have a choice of which way is the easiest way to go to calculate this. And just looking at this, to me, I think it might be using the upper half. Okay. And if we did that, I'd draw my adjusted free body diagram. Okay. If we cut it here, it's still going to have a little bit of projection out. Again, this is linear, so this is still going to be going in that direction. So my H still has to be going in that direction because this and this make it want to go counterclockwise. This and this want to compensate for that and make it go clockwise. So my H is equal to FQX over I, same F, same X, same I. Now we need to do Q. Q is equal to the area cut off times the centroid. If I look at this upper half, I'm going to have this little section. And what is that area? That is going to be, if this was 9 up for the baseline, this is 5 plus 6 up to the top. So that's 11. So this little side is 2, this little side is 2. So the area is 2 times 2, plus the area up above, which is 1/2 times 6 times 4. Wow, that was easy enough. What about Y bar? Y bar is going to be another little neutral axis. Okay. So a couple ways you can do that. I would always recommend you go back to the baseline because that's a standard. You know that's not moving on you. So, so this is going to be the summation of the areas times their centroids divided by the sum of the areas. Let me erase this a little bit here. Okay. So if I look at this little section, that area is 2 times 2. And what is its centroid? It takes you 6 to get to, 5 to get to here. This is 6, but it's down 2, so it's 4. So that's going to be 5 plus 4. 5 plus 4. Plus the area of the top, which is 1/2 pi times 6, 1/2 6 times 4, times this centroid, which is from here to here, it takes you 5 plus 6. It's going to be 11 plus the 4 over 3 again. All of this divided by 2 times 2 plus 1/2 times 6 times 4. Okay. This is the area. When you do this algebra, this is the Y bar. So if I multiply this times this, I have this. So this times this is this. To substitute back in here to come up with my H value. And I've already determined which way that has to go. Could you have done it the other way? Absolutely. You could have said, let's look at the H, it's below this. So I'd have to look at this area plus that area. So I'd have to get this area, add it to this area to come up with my total A. Then I have to find a new little neutral axis for this guy. And again, I'd use a baseline. So it's this area times its centroid. This area times its centroid divided by the area. You come up and lo and behold, when the dust settles, you're going to have the same value for H, except when you do the lower half, this guy's going the other way. So But you always have a choice of doing it either way. And remember, you can always cut this anywhere you want to, just like before when we had something and we cut it here to find shear stresses, plane stresses. Whenever we do this, we can always do a left-hand side, we can do a right-hand side. We could look at any side we wanted to, as long as you use the rules for free body diagrams, and you know it's going to balance out because it's in equilibrium. Again, you could do a left-hand side, you could do a big right-hand side, you could do a right-hand side, you could do a big left-hand side. You're still going to come out with the same values. And you know when you do it in equilibrium, when you put them back together, they cancel out. When you put them back together this way, they cancel out. Just always take advantage of your free body diagram, and you're drawing your free body diagram from looking at the 6 equilibrium equations. Did I miss a question there from someone? That's the problem. Unless you say something in your microphone, I don't know it. And sometimes when you put the little bubble questions up there, it's gone by the time I turn around to look at it. So, everybody feel, should I say, more comfortable with that? Where does the 5 plus 4 coming in? Okay. This semicircle had a radius of 5. So it takes you 5 to get from the baseline to the bottom of the rectangle. The rectangle is 6 high, but we cut it 2 from the top. So this is 5, and this is 4 to come up with the 9. Another question. Okay. The answer to the extra credit one was I guess, where's H the largest value? And H is going to have, H max is at the neutral axis. So wherever the neutral axis is, whether you cut it and look at the top half or the bottom half, this will always have an H max value. And where's the minimum going to be? It's going to be if you cut it at the very top or very bottom, and it's going to be 0. Okay. Any questions on that quiz? Okay, I'd like to start on the next topic, which is Mohr's circle. Give me a second to erase this. Before I started the Mohr circle, about 15-20 minutes before the class was to start, I sent you a solution to reactive theory exam number 3. As you might expect, it was a little lengthy. It took 2 pages to show out the solution. That's correct. The total height of 6 was 4 and 2. I usually grade exams, particularly if I get them on a Friday and they're due back on Monday. I grade them on a Sunday while I'm watching football games all day. And when I finished up grading last night, because it took me most of the day to do that, I don't think anybody had the same numbers. And sometimes it's very difficult to see where you came up with numbers. You would apparently have the right numbers, then you multiply, divide, take a cosine, whatever, and then all of a sudden, I wouldn't know where that number that you got came from. So I try to be consistent when I grade. So when I finished up last night, I had them all graded. I had a high, I had a low, I had an average. And then this morning when I got up, I thought about it and I said, I wonder if I graded consistently what I went through. Because what I do again is if you make a mistake, I will take off for that mistake. But then if you carry that mistake all the way through the rest of your equations, and your logic path, I will not take off for it again. But I had a feeling when I glanced at a couple of them this morning that I was not uniform in my grading. That in one place I might have taken off 4, another place I might have taken off 2. It was really the same thing, but on different papers. So I decided I wanted to go back and relook at everything to readjust, if necessary, your grade on that exam. So I am pretty sure I'm not going to be able to finish those up this afternoon because I'm going to grade the 2 quizzes you gave me today and put those in the box before I leave tonight. I'm probably coming in tomorrow afternoon, so I will hopefully be able to finish up and put your exam in the box tomorrow afternoon. If not, it will definitely be there Wednesday morning. As soon as I put them in the box, I will let you know. As far as the 2 quizzes you've given me today, those will be graded in the box tonight before I leave. Any questions on that? Okay. The grades overall were pretty good. Most people did very well. There was a couple of people that didn't do well, and by well I mean they got in the 70s or 60s, and that was primarily because you didn't show me how you did what you did. So if you didn't come up with the right answer, it was very difficult for me, almost impossible for me to figure out what you did. You know, did you put a cosine in wrong, or did very difficult to follow. So that's part of the reason I'm going back and looking at things again. Okay, let's look at Moore's circle. And this is the last topic that will be on exam number 4 for nuclear material science. I am giving you a quiz to take home. It'll be due for class on Wednesday on a Moore circle. So, Moore circle is a graphical technique to quantify plane and shear stresses in a system by looking at a small cube in that system. Okay. Let's say I gave you a beam or a bar where sigma x was equal to 50 megapascals, sigma y was equal to 10 megapascals, and tau xy was equal to minus 20 megapascals. One of the first things I might do is ask you to show these stresses on our cube. So if I sketch my cube, okay, if we look at this, this is the plus x face, therefore this is the minus x face. This is the plus y face, so this is the minus y face. We know the system is equilibrium. So it says sigma x plane stress is plus 50 megapascals. So I know on my plus x face, I can sketch in that value, but this is 50 megapascals. It's going in that direction because it is plus. Because of equilibrium, I know that I have to have that exact same value on the backside. If I look at the plane stress for y of plus 10, this is the plus y face, so this has to be going up like this. 10 megapascals. By the same logic for equilibrium, this has to be going down 10 megapascals. If I've drawn this correctly, since this is 50 and this is 10, this vector should be 5 times that for that vector. I'm not quite that precise up here, but I wanted you to realize that. So again, 10 and 10, it's in equilibrium. If I look at this, this is the shear stress acting on the plus X face due to a shearing force in the Y direction. This is minus 20 megapascals. So because of the minus, I know it has to be going down like this. For equilibrium, I know that this guy has to be going like this. If we draw this for equilibrium, I should also put up here 20 megapascals. I do not have to put the minus because the direction of the vector shows me what I'm doing. So in this particular case, this is going to be going back up here. This is going to be going in this direction due to equilibrium. So I can also put over here 20 megapascals. So my little cube, but I'm only showing a square of it, is in equilibrium. I've drawn in the respective plane and shear stresses that exist on this. And this is what I have as far as a free body diagram that defines equilibrium. This looks very messy to work with. So typically what we do is we only show what's going on the plus X and the plus Y face. Yes, this other exists and is true, but we don't use it. We just go with that. So I'm going to resketch that over here. Okay. So I don't need this anymore. Now that we've established taking the stresses, putting them on the cube face, we can go back and now create a Morse circle. And there's a little cookbook that you do to use that. Okay. This is the X and the Y, except this is going to be plane stress and shear stress. Okay? So what we do, okay, is we take sigma X plus sigma Y, we add those two together, divide by 2, and this creates sigma average. And sigma average is the center of our Morse circle. So in this particular case, we have 50 plus 10 divided by 2. So that's 60 divided by 2. So that is 30 megapascals. So if I come on this plot, I can go over, I want to denote 30 megapascals, so I can go 10, I can go 20, I can go 30. So right there is sigma average, and it is the center of my Morse circle. The next thing I need to do is to plot the values of the plus X face. So what is the plus X face? This is the plus X face. So I'm looking at those values. When we do this, sigma X plots as is, tau XY plots as the negative value. Okay? So if I come over here, the plus X face, what is here? It is plus 50. So 10, 20, 30, 40, 50. And then this says it's minus 20, but we say we have to have the negative value, so we reverse it. So it becomes plus 20. So 10, 20. So this value is the plus X face. And what I'd recommend you do is denote the coordinate values. So this is 50 and 20. So again, we're plotting the values on the plus X face. Keep sigma X as is. For the shear stress tau, take that value and you reverse it. Make it a negative value. So this is now the plus X face. This is the average value for plane stress, which is the center of my Mohr circle. So if I connect these two, what do I have?
The radius of your circle?
Radius.
Absolutely. This is the radius of the circle. Okay. So excuse my my drawing here, but it's going to look something like that. Hopefully better than that. My drawing isn't too good here. But we can find out what this radius value is by looking at the little triangle, in particular the little right triangle that we have. So what is the radius? The radius is equal to the Pythagorean theorem, this value of x, which I'm calling the difference between x's, between this x, and the difference in y, which is this y and that y. So that's, this side is 50 and 30, so that's 20 squared. This side is 0 and 20, so that's 20 squared. So this is the square root of 400 plus 400 is equal to the square root of 800, which is, somebody have a calculator before I get mine out?
$28.28.
Yep, thank you. So this is 28.28. So this value is 28.28. Okay. So what I'm going to do now is I'm going to erase this.
Does that value have a unit associated with it?
You can consider it to be megapascals.
Okay.
So we'll make it megapascals. Okay. So what I'm going to do now is I'm going to erase this upper part. And if you're finished with writing these first two things, I'm going to erase that too. Okay. So, for the next thing I'm going to do is I'm going to identify sigma max and sigma min. How would I do that? I would take my average value, and if I add to it R, Because what I'm going to do is I'm going to swing this radius down to the sigma axis. So this point is sigma max. If I rotate it all the way back the other way, this value is sigma min. So sigma max is equal to the average plus R, which is equal to 30 plus 28.28. So that value is 58.28 megapascals. So this point right here, sigma max, is 58.28. That is the value for sigma. What is the value for tau at that point? Looking at Moore's circle.
Well, it would be rotating the radius until it was vertical, then doing the math from there.
I think it would be 1.72.
I wrote. Say that again?
I got
I'm rotating-
1.72.
No.
If you're going back to the
No, I'm not
the x-axis.
I'm rotating the plus x face to show the maximum value for plane stress. I've just done that. So you've rotated this point down to here. So what is the value of shear stress when I have my maximum value for plane stress? From just looking at the plot.
0.
0. So I've rotated the plus x face clockwise down to this point, so that would then have on that face this value for plane stress, this value for shear stress. And that is the maximum value for plane stress. If I wanted to find the minimum value, I would take the average value and I would subtract. I would rotate this point around to here. So sigma minus R, so 30 minus 28.28. So that value was 1.72 megapascals. So this point right here is sigma min, and we automatically know that it is 1.72. I always encourage you to put in the coordinate values. So if this is 1.72 for sigma min, what is tau at that point?
It would also be 0.
Also be 0. And how do you know that? Just look at this plot. That's why I'm recommending you put in the coordinate values, because right here, this is 1.72. This is on this axis, so it's 0. So we know right away that sigma max is 58.28 megapascals. We know sigma min is 1.72 megapascals. If we know what material this is, let's say it's aluminum 1100, I could ask you, is this system safe? I would look at my maximum value, and that is less than the yield value, which is 95 megapascals. So this thing is safe for plane stress. All right. I now might want to find out my tau max and tau min values. And how do I do that? If this is the tau axis, I want to rotate this point till it's exactly above my center. And this is going to be tau maximum value. If I rotate this directly below, this is tau min value. Okay? So if I rotate, again, my plus X base up to here, so that's going to show tau max, what is the tau max value when I rotate this point up to here? What is that value?
Well, that is the radius, so 28.28.
That's the radius, so it's 28.28 megapascals. How about when I rotated it down here to the minimum value?
Negative radius, so negative 28.28.
Negative 28.28 megapascals. So I know the max and the min, so I now, if I look for the yield value, and I know for my aluminum 1100 is 55 megapascals, this is less than this, so this is also safe. So I know for this loading, my system that I've taken a little cube out of is safe. Now, the other thing I'd recommend that we do to get a better idea of what's happening is again, this is sigma max, but I want to denote what its coordinate values are. So if we are here for sigma max, what is my plane stress sigma value?
$30.
30 megapascals.
Exactly. Because where is it here? It's directly over sigma average. So this is 30. What is my shear stress value? We've just said it's R. If I go down to the minimum value, what is my sigma value there?
It would be 30 as well.
Absolutely, it's 30 because it's directly at sigma average. What is my tau value for shear stress?
Negative 28.28.
Exactly, minus 28.28. Okay. If you take the stresses I gave you, put it on a cube, and then translate it to a Mohr circle, this, which we have just sketched, because you've established a circle, and you've identified the points of interest, which is sigma max, sigma min, tau max, tau min. This is a complete Mohr's circle. Okay. Now, something you might want to do after that is show how these values would occur on our cube. Everybody with me so far? Hopefully. Okay. So I'm going to erase this. And the next question I might ask you is to rotate the circle and the cube to show sigma max on the plus X face. Okay. One thing hopefully you picked up on is no matter how we rotate our little cube here, wherever we stop the rotation, so if we took this and we rotated it 30 degrees, so plus X goes down here, plus Y is there. We can find the values for plane and shear stress on either of these faces. And if you do that, no matter how you rotate the circle, clockwise, counterclockwise, wherever you rotate it, the plane and shear stress values will always be on this circle. So in other words, whenever you rotate it, it can never be off the circumference of the circle. It can never be out here. It can never be in here. It must be on the circumference of the circle. Okay.
So typically you would be given an amount of rotation and direction.
Well, that's what we're going to do now.
Okay.
So what I've asked you is to rotate the circle and the cube to show sigma max on the plus x face. This is sigma max. So if I look at my circle, I want to rotate this down to here. How far is that rotation? I need to know what is that angle. And I can do it a number of ways. I know this side, I know this side, I know this side. Probably the easiest thing to do it is I know this side, and they were both 20. So I know the tangent of theta is equal to the opposite over the adjacent, is equal to 20 over 20, is equal to 1. So theta is equal to the inverse tangent of 1, which is 45 degrees. So I know this value in here is 45 degrees. If we look at the relationship between the circle and the cube, this is the plus y base where we have this value. If you rotate it down to show a minus y base, you're going to have the exact same value. Where this was 10 and this was 20. So when you rotate the circle, so we're going to rotate our circle 45 degrees clockwise. Okay? If we look at this and we take the plus x face and we rotate it here on the cube 180 degrees, we'll get exactly this same value on this side. If we take the circle, how far do we have to rotate the circle to get exactly that same value again? So if I rotate this face 180 degrees over here, I'm going to get that exact same picture. If I rotate the circle, this point right here, how far do I have to rotate it to get exactly the same value?
$180 degrees?
No. 180 degrees would be down here.
360 degrees?
360 degrees. Okay? So if I rotate the circle 45 degrees, I'm going to rotate the cube half of that, which is 22.5 degrees, and it still has to go clockwise. So whenever you rotate the circle, if you rotate it half as much, you will find out what the value is on the cube. Since somebody mentioned 180 degrees, If I go 180 degrees from here, so it's right here, what is 180 degrees from the plus x face on my Moore circle? Go back and look at my cube. This ratio is what? 2 to 1. So that's going to hold wherever you go. So when I rotate the plus x face 180 degrees, how much have I rotated the cube? Deathly silence out there.
90.
Yes, Heather.
90. You've rotated 90.
90. So if I rotate this 90 degrees, I have what? I have the plus x face. So if I rotate, if this is the plus x face, if I rotate down here, this is the plus y face. Because this is 180 degrees, this is 90 degrees. We have to keep that 2 to 1 ratio. If we look at this, where is, on this circle, where is the minus x face? So here, it's right here, for plus x. Over here, this is minus x face. Where is the minus x face on my Moore circle? Anybody? If I come here, I have rotated this to get to this point 180 degrees. With my 2 to 1 ratio, it has to be twice that of 360. So if I rotate this, this is also the minus x face. Because if I rotate this 180, I have to do the 2 to 1 ratio. So the 180 goes 180 degrees becomes 360 degrees. So if I go to rotate cube, so I started like this, where this is the plus x face, this is the plus y face. Okay. And to rotate the plus x face to show sigma max, I've had to rotate this 45 degrees clockwise, which means I have to rotate the cube half of that, or 22.5 degrees clockwise. So that means I have rotated this plus x face 22.5 degrees clockwise. So this is now the plus x face, because I've rotated it 22.5 degrees. This is the plus y face. This is the minus x face. This is the minus y face. I've rotated this plus x face 22.5 degrees clockwise down to here, which was 45 degrees here. When I rotated this, I'm showing sigma max on the plus x face. And what is that? The maximum value is 58.28. It's positive. What is the shear stress on this point? It is 0, so there's nothing going in that direction. If I've rotated this 45 degrees, I've rotated this 45 degrees. So this is now, the plus y face is moved up to here. So what is on the plus y face, which is right here? If it moves up to here, I'm going to have 1.72. It's going to be just a little nubby here. 1.72. The shear stress is 0, so that is correct. So I have rotated the cube to show sigma max on the plus x face. If I look at this, this tells me at this orientation, I have my maximum value. So if our cube fails, it is at this rotation of 22.5 degrees clockwise from its initial. So if I take this orientation, okay, and this value was 22.5 degrees. This 22.5 degrees is called the principal axis. If it fails, it will fail on that axis. So if we started out with our original cube, and this with its loading is due to fail, it will fail at an angle of 22.5 degrees. It'll just pull apart like you had taffy. So not only can you identify what the maximum value is, so you can look at, does it fail, but you can actually tell how it's going to fail and where it's going to fail. Okay? Let's look at a different version of this. And I realize you might have a lot of questions on this, but let me just leave this as is right now. Okay? Let's say the next thing I'm going to ask you is, rotate the cube and the circle to show tau min on the plus x face. Okay. If we come back to our Moore circle, this is the plus x face. This is tau min. So we need to rotate this point down to here so that you can show this tau min value on that. There are two ways you can do that. Since this is a circle, you could rotate it this way, which is clockwise. You could rotate it this way, which is counterclockwise, and you're going to get the exact same answer. So you might as well do the one that is easiest. Let's look at rotating it clockwise. So I want to rotate the circle clockwise to show tau min. So how far am I going to rotate that? It's going to take you this angle, which is 45 to get to here. To get to here is another 90. So I'm going to rotate this 45 plus 90, or 135 degrees clockwise. Therefore, I'm going to rotate the cube half of that, which is going to be 67.5 degrees clockwise. So if I go back and look at rotating this, this is my original cube plus x plus y. I now tell you I'm rotating the plus x face 67.5 degrees. So this is the plus x face. This angle is 67.5 degrees, and I'm rotating it clockwise so that my new little cube looks like this. This is the plus x face. This is the plus y face. Okay. When I rotated that, what is sigma value on the plus x face? I rotated the plus x face from here down to here. So what is that value that I'm going to put on the plus x face?
It would be 30, no?
It
So
will be
at
30.
that point, we're 30 minus.
Exactly.
Right.
I've rotated it 45 plus 90 down to here. So this is the plus x face. I moved to here. So all we need to do is read the coordinates off of this. So this value is plus 30. And again, I let my vector do the talking. This would not be correct because you always show a minus by the direction of the vector. So it's going to be plus 30. What is the value of shear stress on this plus x face?
It'd be 28.28 with a minus sign.
28.28. So I have a choice of either putting it in this way or this way. Which way am I going to put it and why? Am I going to put it this way, why, or this way, why?
The arrow that's pointing to the left because it's a negative value?
No,
No, okay.
it's going to go this way because remember when we first set up the Moore circle, we took whatever this value was on the plus x face and we reversed it when we plotted it on the circle. So this was minus 20 here, but when we plotted it here, it became plus 20. So it has to be going in that direction because this is a minus that says to show as a plus, but we know its value is 28.28. Because of equilibrium, I can immediately, and this is the plus y face, I can immediately draw that in that way. So that just leaves us, what is the value of plane stress on the plus y face? And if I move the plus x face down to here, and this is the plus y face, has to be exactly opposite. So it's rotated up to here. So what is the value of plane stress on the plus y face?
Zero.
Heather? No. Remember, look at where it's rotating. This is the plus y face. We've rotated the plus x face 67.5 degrees. So this has to go up to here. It's going to end up here. Remember, the plus y face and the plus x face in this sketch are always 180 degrees apart because here they're 90 degrees apart. Second guess.
1.72.
No, 1.76 is right here.
I'm all out of guesses.
Any other guesses? Chris?
It would be where the it'd be 30.
Correct. It is 30. And again, you know that because this rotates up to here. What are its coordinate values? These are its coordinate values. So we're going to have to plot that on this. Let's try one more, and then we'll, let me just try it on this one. Okay, let's erase this. So I want to rotate the circle and the cube to show tau min on the plus x base. Okay? So this is the plus x base to start with from this orientation. I want to rotate the circle and then rotate the cube to show this is sigma min. And I've erased it, but that was 1.72 and 0. Okay? So I want to rotate this to here because I want to rotate this to show the plus, this value on the plus x base. Again, I have two ways I can do it. I could rotate it this way to go clockwise, or I could rotate it this way to go counterclockwise. Just to do it different, let's rotate it counterclockwise. So I'm going to rotate the circle. From here to here is 45. From here to here is another 90. So this is going to be 45 plus 90, which is 135 degrees, and I'm going to rotate it counterclockwise. Therefore, I have to rotate the cube half of that. And again, I've rotated this counterclockwise. So if I go back from my original orientation, plus x base plus y base. This is what I'm starting out at. So I've just found out that I have to rotate this plus x base 67.5 degrees counterclockwise. When I do that, this is my plus x base, this is my plus y base. I've rotated the plus x base 67.5 degrees up to here. The plus y face rotates to there. This is minus x, this is minus y. So when I've rotated my plus x face up to here by this amount, what is the value of plane stress here? Anybody?
1.76.
1.76. Okay. So I'm going to have very small 1.76. Has to be going that way because it is positive. Okay. What is my value of shear stress now on that plus x face?
0.
0, and you know that because that's the other coordinate value here. So it's 0, so it doesn't even show up. If I look at what's going on the plus y face, when I rotated the plus x face down to here, the plus y face, which was originally here, rotates all the way around to here. So this value is going to show up on there. So my plus y face has gone from here around to here. This point coincides with this point on the circle. So the plane stress is positive 58.58 megapascals. My shear stress is 0. So this is the rotation of my cube to show sigma min on the plus x face. And again, anywhere you rotate this, however you rotate it, it can never leave the circumference of the circle. So if I rotated this down to this point right here, I could find out what this angle is. Let's call this angle alpha. And whatever this is, this would show you a sigma and a tau value on my rotated cube. Let me do one more quickie here and then we'll take a break, but I'll give you the quiz before we go out. Any quick questions on this while I'm erasing? All right. Okay. Okay. Let's let one of you pick 3 values. And you know, think about mixing up pluses and minuses. Don't do it the same way we did the other sample problem. Anybody? Give me a value for sigma x.
$248.73.
You're going to make this really difficult to draw that circle, aren't you? Let's try a different one. Let's make them smaller numbers. They can still be positive or negative. I could do that, but I might have to expand the blackboard to draw a circle.
7
Plus or minus?
plus.
Plus. Okay, how about sigma y?
-6.
-6. How about shear stress?
-12.
-12. All right, let's draw our cube. Plus x face, plus y face. So on the plus x face, we know we have +7. On the plus y face, we know we have -6. Notice I don't put the minus, I let the direction of the arrow. This is -12, okay? So minus means it's going to be going down in that direction. And again, I just put in the 12, I don't put the minus because that will define what's happening, okay? I'm now going to draw my Moore's circle. So the first thing I need to do is find the center of the circle, which is the average, which is sigma x plus sigma y divided by 2, which is 7 minus 6 divided by 2, which is 0.5. So that center is like right there. So that is, sigma average is at 0.5 megapascals. I then need to draw the plus x face. What is happening on the plus x face? I know it's +7. 2, 3, 4, 5, 6, 7. And this is -12, but I know I plotted as +12 because you reverse it on the plus x face. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this point is the plus x face, and it is exactly 7 and 12. If I connect the center of the circle to the plus x face, I have the radius. I can calculate that radius because I know the radius is equal to the square root of the difference of x's squared plus the difference in y squared. What is the difference in x's? This is 0.5 and this is 7, so that difference is 6.5. Is that side of the right triangle squared. Plus this side is 0 and 12, so that's 12 squared. So this is 42.25 plus 144. So it's going to be the square root of 186.25, which is, let's just make this 13.6. So this side is 13.6. this is my center of the circle and this is my radius, if I swing that in a circle, I can immediately identify sigma max, sigma min. Directly below this would be tau min. Directly above this would be tau max. It would be nice to identify what those points are. So at sigma max here, we know that sigma max is equal to sigma average plus R, which is 0.5 plus 13.6, which is going to be 14.1. So this is 14.1, and since it's on this axis, it is 0. Likewise, if we come this way, sigma min is equal to sigma average minus R, or 0.5 minus 13.6, or minus 13.1. So this value is minus 13.1. And again, it's on this axis, so it's 0. If I go directly down, tau min is going to be tau max is equal to tau min is equal to R is equal to 13.6. So this guy is 0.5 and 13.6 minus. This guy is 0.5 and plus 13.6. I've now drawn a complete free body diagram. Okay. We'll just do one of these very quickly. Any questions on how I took plane stresses off the face, drew them on a circle, and came up with all the points of interest, which are the center of the circle, sigma max, sigma min, tau max, tau min. Let's say I wanted to rotate the circle to show sigma max on the plus x base. So this is the point. So I'm going to rotate this point to here. So if I find out this angle, let's call this angle alpha. So the tangent of alpha is equal to the opposite over the adjacent. The opposite is 12. The adjacent was 6.5. So I have alpha is equal to 61.6 degrees. So this angle here is 61.6 degrees. So if I want to move my plus x face to show this value, I'm going to rotate around the circle. And I could go it all the way this way. It's easier to go it that way. So I'm going to rotate the circle. If this was 61.6, to go the rest of the 90 degrees, that is going to be 28.4 degrees counterclockwise. So I'm going to rotate the cube half of that. So that's going to be 14.2. So if I come over here, my original Mohr circle, where this is plus x and plus y, I'm going to rotate this 28.4 degrees counterclockwise. So I then rotated my plus x face up to here. My plus y face goes over here. What is on the plus y face when I've rotated it here? It is this value, which is minus 13.1. So we draw it coming in because it's minus 13.1. What is the value of my shear stress? 0. So there's nothing going across his face. What's the value on the plus y face? If I've rotated this point down to here, the opposite is rotated around to here. So it's going to be this, plus 14.1 and 0. So this shows the orientation. If this is going to fail, we can look at this angle as the principal axis. So if it fails, it's going to fail along that line. It'll appear just as if you're pulling taffy. Okay. We did that one quickly. What I'd like to do now is I'd like to send you the quiz that will be due on Wednesday. Okay, I just sent you the quiz. Let me know when you got it, and I'll go over it with you very quickly, and then we'll take a break. Okay, let me know when you've opened it up. Alicia, is your hand up? Is that what that? Okay. Okay. So for 8 points, I've given you a cube that has the following stresses applied. Sigma x is plus 30, sigma y is minus 10, tau xy is plus 25. I want you to draw a cube showing those stresses. I then want you to draw or sketch in a complete Mohr circle identifying the important points. Important points are the center, sigma max, sigma min, tau max, tau min. I then want you to rotate the cube to show sigma max on the plus x face. So rotate it and give me this type of relationship. Then I want you to rotate the cube to show tau min on the plus x face. And then if you're up for extra credit, I want you to rotate the cube to show exactly the plane stress is equal to 0 on the plus x face. So do the regular quiz. My guess is it might take you 10 minutes tops. The other one is going to take you a little bit longer because you've got to realize what you're doing. To give you a little hint there are 2 possible values for that, and I'll accept either one. Any questions on the quiz? Okay. Why don't we take a 7-minute break, and I will see you at 15 after. We're going to do the reactive theory. And just so I know now, is anybody interested in presenting their quiz solution for that to the class when we come back? Any takers? Going once? Going twice? Okay, I will put my solution up when we come back, and I will see you in 7 minutes. Okay, looks like we have most everybody back. So, go up through the quiz. I've asked you to use the full n-hour equation to find the amount of reactivity you would need to add to make the reactor period be exactly 150 seconds. We know that this is the full n-hour equation. This is the shorthand, because this is showing you're summing all of the beta sub i's. So down here, I put the first part, and beta 1, 2, 3, 4, 5, 6 to account for everything. And what I've done is I've just gone back and shown you the values for the first couple. So when you do this, this is always a prompt group. And because of that, this L value is always going to be 10 to the minus 3. And if you want to think of it, that's the lifetime of the neutron as it's slowing down. K effective is 1 because we always want to operate at or around 1. Then in this particular case, my T value is 150 seconds. When I go to look at the contribution, this is delayed group 1. So for the beta 1 value, I'm going to take whatever that value is from a table I've given you, which is typically in a percent, and then I have to add 2 zeros in front of that to make it a real number. So beta 1 from our table was 0.023, so I have to add 2 zeros to come up with that. Divide this by 1 plus lambda 1. What is lambda 1? Lambda 1 is 0.693 divided by the half-life of that precursor group, which in this case was 54.54. I would do the same thing for 2. This is the beta value. This, put the 2 zeros in front. Down here, 0.693 divided by 24.62, and again, times 150 seconds. I do the same thing for each of these. When I did all of that, and then I did the algebra for adding up all 7 of those contributions, I had rho was equal to 3.378 times 10 to the minus 4th. And if you noticed, this is in seconds, this is in seconds, cancel, cancel. So it's dimensionless. Whenever it's dimensionless, your answer is in hours. If I divide this value by my beta 1 to 6 value, which was 0.00264, again, I had to add the two values to take it from a percentage to a real number. So if I divided this by this, my reactivity was 0.1279 dollars. I then ask you, this was the full in our equation, so you know this is an exact answer. I then ask you to use an approximation value from the table in the book, and the reactor period of 150 seconds falls in that middle grouping. And the middle grouping is L over K effective T plus beta L sub D over L sub D plus T. If we go back and substitute in values, this is the same as this. This is always 10 to the minus 3 seconds. This is 1. We know we're looking at 150 seconds. Beta is the sum of all your betas, which is this number, which is 0 point in 2 zeros to put it into a real number. LD bar was what we calculated back in the quiz before this, which was 21.39 seconds. This again is 21.39 seconds plus my reactor period, which is 150. So if I do that algebra, I come up with my reactivity is 3.362 times 10 to the minus 4th. Again, cancel, cancel in hours. So this is the approximation value for this. I'd say that's a pretty good approximation. 3.378, 3.362, all times 10 to the minus 4. So that's a very good approximation value. Any questions on either part of that for the quiz? The main things to remember is to put your 2 extra zeros in here, and then make sure you make your correct lambda. All right? And then for the last part, I ask you, if a precursor produces a neutron during its decay and that half-life was 8.12 seconds, which precursor group was it involved with? If you go back, beta 1, 2, 3, 4, 5, and 6, and I gave you a range which each of these act in. For example, when we did this one for the uranium-233, this was the average value for a precursor half-life in group 1. It could be a little higher than this, it could be a little lower than this, but that was the general ballpark. If you go down, 8.12 seconds fell within the beta 3 group. So the answer to that was, it was in the beta 3 or the third delayed neutron group, was where that precursor would be located. Any questions on anything to do with that quiz? Again, a little bit of algebra, a little number crunching, but hopefully readily easy to do. Anybody think they'd have any problem calculating reactivity required to establish a period of a particular time for using the full n-hour equation? So you're going to come up with 7 different parts that you have to do the math on and then add them together. Any questions on that? Okay. The next thing I'd like to go over is reactivity changes with temperature. And this is called alpha sub T, and it's looking at the change of reactivity with change to temperature. And this is called the temperature coefficient of reactivity. We know reactivity is equal to K minus 1 over K.
Does it say P or E?
What'd you say, Joel? I'm sorry. You're
Is
breaking
that-
up a little bit.
What is that minus 1?
This is your K value, or you could also put in your K effective if you want to, because you tend to operate around.
No, I'm saying, what is that an L? I don't know what that is.
What I'm looking at is I'm going to take the rate of change of reactivity. Well, I took the definition of reactivity, which you could make this K effective minus 1 over K effective. But this is delta K effective. Since this is 1, reactivity is essentially equal to delta K effective. And what I'm looking at is I'm going to look at small changes, because that's how we tend to operate the reactor, is very small changes. So I'm looking at reactivity, and I'm going to look at how does that change with time. And if I do that, I'm going to come up with, I'm going to separate this. So this is going to be K over K minus 1 over K. So this is 1 minus K to the minus 1. If I take the partial of this with respect to T, partial of a constant is 0. If this comes down, minus 1, K to the minus 2. So this is equal to, minus and minus is plus 1 over K squared. K squared is effectively still 1, because 1 squared is 1. And we know that K is always positive. So the bottom line, when you look at this, and you can follow this in the book, and they're showing you how they do that, is if the coefficient is positive, then the rate of change of K with T has to be positive. So if K goes up, T has to go up. If alpha T is minus, the rate of change of K with respect to T is also minus. And what this means is that if T goes up, K goes down. Okay? And the upshot of this is, I'm not going to hold you responsible for doing that derivation, but what I'm interested in you realizing is this relationship. Okay? If the temperature coefficient for reactivity is negative, then as the temperature goes up, my K value goes down. So if you would, this is self-regulating. So if we had alpha sub T being positive, if the temperature goes up, K goes up. If K goes up, the temperature goes up. So this could very well be a runaway situation. So all commercial reactors must have a negative alpha T to be licensed. No exceptions. Okay. If any of you have ever looked at or read in depth about what happened at Chernobyl, what happened at Chernobyl was in regular operation of their reactor, alpha T was negative, which is where it should be. And what they decided to do is they wanted to see if a reactor had scrammed and that you were at basically a very low residual power, would there be enough power to operate the auxiliaries to, for example, pump additional water in to cool things off? So they hardwired all the safety systems so that when you got down to around zero power, the emergency systems like high pressure injection, low pressure injection, all those safety systems could not operate. They were hardwired shut. And they wanted to see if they went down to essentially zero power when it tripped, was there still enough residual power to run the pumps or whatever so they could keep it going and minimize the downtime to get it back up again. What they did not realize, first of all, they did it in the dead of night, so there were very few people there. And some engineers came up with this idea, and they got the operators to do it, is when they drove the power down to around zero, the temperature coefficient flipped and became positive, so that the temperature started to go up, K went up, K went up, T went up, T went up, K went up. All of a sudden, it was a runaway situation, and they could not activate any of the safety systems because all of the safety systems had been hardwired, so they could not activate to shut the reactor down. So what did you have? You had the catastrophic event that was Chernobyl. All because of this. So any commercial nuclear reactor must have a negative temperature coefficient for reactivity so that it cannot run away. In real life, there is one exception to this. Does anybody know where alpha T can be positive? Anybody want to take a guess? Nobody? There's some heavy breathing out there, so maybe somebody's thinking about it. Any guesses? Okay. The one exception is military reactors. So if you're on a nuclear submarine, you're on an aircraft carrier, and all of a sudden you have a loss of power, you do not want this negative temperature coefficient to come into play so that you can't raise the T and raise K. So in other words, you don't want to be dead in the water, so you're sitting duck for whatever might be after you. So the only exception are military reactors. Okay. Any questions on that? The other thing I wanted to cover today, get my notes here. Okay. I wanted to go through poisons with you. So any questions on that? Okay. What is a poison? Poison is a substance that has a large absorption cross-section for thermal neutrons. So that could be good. For a poison, if you want to shut down a reaction, you can put in something that has a very large absorption cross-section. That's going to remove a lot of thermal neutrons. It'll induce a negative reactivity, and you're going to shut things down. However, if you're trying to operate things regularly and you have something that has a large thermal cross-section, it's like a black hole for thermal neutrons, and you're going to have to account for that to make sure your system remains critical. Does anyone know what the worst poison is? Professor Abel might have covered this, I'm not sure. Anybody know what the worst one is? Yes, it is xenon. It is xenon 135. And sigma absorption for thermal neutrons is 2.72 times 10 to the 6th barns. That is huge. So if you have xenon 135, and unfortunately xenon 135 is in the decay chain for fission fragments for thermal fissioning, so this is a problem. If we look at xenon 135, it is in the decay chain. It starts off as tellurium 135, goes to iodine 135, goes to xenon 135, goes to cesium 135, goes to barium 135, which is stable. All of these decay by an electron emission. This half-life is negligible. It's actually 19 seconds. This guy is 6.6 hours. This guy is 9 hours. And the final guy is 30 years. Okay? When you have Remember, this is about 2.5 neutrons. We have 2 fission fragments, and typically for uranium-235, there are 16 pairings. You'll find out that one of these pairings is iodine and something. Another pairing is xenon and something. So when you have a fissioning, you will have a certain amount of iodine-135 that is created. It is unstable because it's radioactive. It wants to decay to become stable at barium. So it's going to decay down this chain. You also have simultaneously, as one of these pairings, xenon-135 that is created. It also wants to decay to go down in that direction. So when you look at this, these two are a sizable object to getting the reactor started up again. If you have a trip, okay, you're going to have a certain amount of iodine-135 that has been created. This must decay away. And remember, when this is in there, this is a poison, so it is sucking up thermal neutrons. You're also going to have xenon-135, and that has to decay. The iodine actually has to decay through xenon, become stable. The xenon can just go on its own. So when you scram, if we look at, say, xenon levels, if you're operating steady state, let's say this is 100% power, and you scram, you're not generating any new xenon-135, but all the iodine that's in there has to decay to xenon. All the xenon has to decay to cesium. So when you scram, this steady state value, which always tends to be there because you're producing new xenon, it's decaying. Remember, you could actually do a rate of xenon with respect to time, which is production minus loss. We could do that to come up with an expression to calculate the amount of xenon. This actually peaks and then dies back off. And for any commercial reactor, the amount of reactivity, negative reactivity associated with xenon trying to decay out is significant enough that you cannot restart the reactor. You have to wait till most of this decays to xenon, and then most of your xenon decays away. So depending upon how your reactor is designed, you're typically going to have, on the average, 9 to 10 hours before the xenon has died off enough that you can restart. So xenon in your system, because there's always some there steady state, and then it increases once the reactor scrams, is something you really have to be concerned with. And we're going to talk a little bit in a minute about what you can do about that. Okay? So the main things I want you to take away from this is the worst poison is xenon-135. Xenon-135 is a direct fission fragment itself that would then decay. It also has as a sort of a mother, because this would be a daughter product, iodine-135, which is a direct fission fragment. All of that has to decay to xenon, then all of the xenon go down to cesium before you're out of the woods with that. But it is something you constantly have to be aware of when you're operating a reactor, particularly if you scram or if you decrease in power, you're still going to have an increase in xenon because of the way the plant operates. The next thing I wanted to go through is the second worst poison. Anybody have any questions about that? Okay. Okay. The second worst poison, does anybody know what that one is? That one is Promethium 149. That decays by electron emission. It has a 54-hour half-life, and that decays to samarium 149. And samarium 149 is stable. There is another radioactive mother, if you would, higher up, which is neodymium 149, which also goes by beta emission, and its half-life is 2 hours. There is a little bit of this neodymium out there, but not very much. So the primary thing is promethium. Promethium is one of these fission fragments that comes from thermal fissioning. So this is a fission fragment itself. It has to decay down to samarium. So this is a poison. It's going to absorb thermal neutrons. Its absorption cross-section for thermal is 40,800 barns. So that is pretty significant also. So when you create the promethium as a fission fragment during thermal fissioning, it's created, it will naturally decay just in one step down to samarium. Okay. Over time, what happens to your samarium if it's stable? You might be able to neutron activate a little of it, but it's not an isotope that is readily activated by neutrons. It's stable. So this just tends, if you did a plot of time versus samarium 149, it builds up over time, and it actually, after quite a bit of time, plateaus. So how do you get rid of samarium 149? Because you just don't want to have your fuel grow more and more to be samarium than other things you'd like it to be. How do you get rid of samarium? Anybody? The only thing you can do is refuel. So when you refuel and you take out the old fuel, you take out all that stable samarium that is built up over time. Okay. Two more things I want to present to you. Any questions on that or on the xenon? Okay. Okay. I picked 3 typical thermal fissioning fuels: uranium-233, uranium-235, plutonium-141. And I've looked at as a direct fission fragment. Okay. So this value is 0.0023, 0.0036, 0.0005, 0.0061, 0.0092, 0.0016, nothing, 0.006, excuse me, 22, 0.0055. So if I look at, I'll just pick uranium-235. If we look at uranium-235 and we look at all the possible fission fragments that come out of that. You know, in any one fission, you have 1 plus 2, and we know that there's 16 preferred pairs. But there are obviously other pairs that don't come up quite as long. If we take, and this, look at this percentage, if we list every possible fission fragment directly that came from uranium-235 and we total up this column, you would end up being 1 to account for everything. So what this tells you is that when uranium-235 undergoes a thermal fission, this percentage of all the fission fragments will be iodine-135. This will be the percentage of xenon-135. This is the percentage of promethium-149. And there's probably, well, 16 preferred pairs is at least 32. So there'd be 32 here in this column and probably more because these are the preferred pairs. But when you look up all the percentages, it'll eventually total to be 1. The same thing if we look at plutonium-141. These are the percentages. So if I look at this, and you have plutonium-141, if you look at this and this, because this decays to this, both of these are going to cause xenon-135, which is your worst poison, which you don't want. For uranium-235, you have this and this. For uranium-233, it's this and this. So when you go to choose what you're going to have for your thermal fissioning fuel or fuels, because you could make it a MOX type thing, one of the things you're going to be looking at is what type of fission fragments am I going to have that can create poisons to absorb my thermal neutrons. One of the nice things about uranium-233 is it doesn't produce any promethium. So you don't have to worry about that poison being there to decay to samarium. So why don't they use uranium-233? Because there are other things you have to consider. What is the reproduction factor? What is the absorption cross-section? Or remember when we went back for, you might have part that's fission, the other part is a parasitic loss that creates gamma rays rather than neutrons. There are all kinds of considerations, but one of the considerations you have to have is that consideration. And if you wanted to look at what the impact of this is, if I want to look at if I look at the reactivity impact due to iodine and xenon, I would look at
And they typically call these, instead of percentages, they use a little gamma. So if I want to look at the negative impact on reactivity due to iodine and xenon, and I wanted to do that for anything, we could pick that for radium-235. To get the reactivity, we would look at these percentages, we would divide it by where this was your resonance escape probability. Remember, your K infinity is equal to so this is the resonance escape probability like you just calculated in your exam. This is your fast fission factor, which is this guy, and this is the multiplication factor that you use in calculating nu in that calculation. So you take this and this, if we did it for uranium-235, we take this and this, add them together, divide by those values, and you know that the reactivity is going to be negative because it's a poison. This is how you can estimate the reactivity impact due to those fission fragments being there. And you could do, and if you wanted to look at the impact on reactivity for plutonium-241, just due to, let's say, promethium, gamma promethium, divided by P nu. Again, that's going to be a negative value. So you have a way of estimating what these are going to be. That would help you design your fuel. That would also help you design what materials you want to use in your control runs. So that was all I wanted to cover today. I have a quick quiz for you on this. I'm going to send this to you momentarily. And when you get that, let me know you've got it, and I'll go over that with you.
Okay. Does that equation that you just put up, does that, is that considers the fact that the iodine 135 is also going to become xenon 135?
Up here, yes.
Yes. Okay.
But that is a good point, but it does.
Okay. Let me know when you've got that, and I will go through that quiz with you very quickly. So let me know when you've got it, you've opened it, and I'll go through it with you very quickly. Okay, thank you. Okay, so the basic quiz is worth 8 points, and then I have extra credit for 2. And this is the 18th quiz for reactor theory. So I've asked you, first of all, what is alpha T? Define it, and then explain to me why it must be negative. Next, for poison xenon 135 and promethium 149, we know that
negatively impact K infinity, what term in K infinity does it negatively impact? I want you to identify that term and tell me why. In the next part, you're operating a thermoreactor at 80% power and you're at steady state. You suddenly scram. How long will it take you to remove all the xenon-135? That's the quiz for 8 points. And then for extra credit for 2, what I want to know is, why are we concerned with iodine-135? That's worth 2 points. Okay. Before we go today, I want to cover what we're going to be doing the balance of the time. These are the last quizzes you've taken. Of course, I can always generate some on Wednesday, do on Monday, just to let you practice a little more, but I'm not going to do that. So, if I look at reactor theory, when you turn these in and I grade this, you will have had 18 quizzes. And if I add together all the points, for example, if I look at quiz number 17, it was 10 points, plus you had the possibility of 2 more. 18, you have 8 points plus the possibility of 2 more. What I'm going to do is I'm going to total up from 1 through 18 what just the basic quiz value is worth. Let's say that comes out to be 254 points. That is going to be my denominator. And then I'm going to add all the total points that you received on your quizzes. So if you've done all the extra credits, and you've done pretty good on them, let's say this number could be, I'll just invent something, 285. I then would divide the 285 by the 254, and that is 112.2. So that is your quiz grade. I then go back, and if you remember how I calculate the grade, I have exam 1, exam 2, exam 3, exam 4, and the quizzes. So let's say you got an 80 on the first quiz, on the first exam, a 92 on the second one, a 90 on this one. You really banged out the quizzes, you got 112.2 on this. And let's say on the exam this coming Monday, you got an 84. I would add those 5 together, divide by 5. I'll do that very quickly. That's 458.2 divided by 5. That is 92. So that's going to be either an A minus or an A. And then I will look to see what you've done for extra credit. Have you done any of the present your quiz solution on the board? Have you done any of the problems that I specifically asked you to turn in, or other mathematical derivations? So let's say this is 92, and let's say it ends up being an A minus. I'll then look to see if you've turned in your notebook. And remember, for your notebook, I'm only looking for problems that you have done at each of the chapters for either reactive theory or nuclear material science. If you don't turn in a notebook, this is your draft grade. That's what's going to show up on the sheet that I'll send out Monday night. So you'll have off to the side whatever your social security number is, the last 4 digits. So let's say 0268. This is you, and this is out here for reactive theory. Your grade is an A minus, unless you want to take the final exam to try to raise it. But if you take the final exam, you could also lower it. So that's how I'm going to come up with all of those. You can do the quizzes just as well as I can because I turned all of them back to you. You've got your other exams. So between now and next Monday, once I've graded these 2 quizzes that come in on Wednesday and get those back to you, I'm going to add up all the quizzes and normalize them for reactive theory. I'm going to add up all the quizzes, normalize them for nuclear material science. I already have these earlier grades. I just have to grade that on Monday, throw that in, and then Monday evening, I'm going to put out that sheet that has your draft grade for the reactive theory and nuclear material science course. You then will let me know if you want to take a final exam. I'll go over more of that on Wednesday when we meet. So this Wednesday, I'm going to go over both the quizzes. I definitely want to do another more circle with you, or maybe even 2 more circles, just to make sure you get the hang of this. I'll wrap up some loose ends in dynamic reactor, and then I'll review anything you'd like to review for the 2 exams, which you're going to do in class on Monday, a week from today. I'll give you the 2 exams to start around 12:15-ish, or whenever you tell me all of you can get together, because I know you're getting out of, I guess, Calc 2 before that. And then I'll let you go up to 3:15 when you have Professor Lance. You can work the exams on any order you want to, but I'm looking for both of them back to me by 3:15. I'm going to grade them. Excuse me, throw the value for in there and then come up with your advanced grades. And then wait to see who wants to do a final exam. Thursday of this week, anytime between now and Thursday, if you want to submit a UOI lab to me to grade, I'll be happy to grade it, get it back to you. And then you'll know how I grade labs. And then you have at least the 5 labs that are due. Plus, if you did the option, excuse me, for extra credit, submit that. And again, I'm just going to add up all of those. I'll go over that again on Wednesday. But if you've already done a lab and you want to look at it, for me to look at it, turn it in. And you have any time through 4 o'clock on Thursday to give me those. I'll grade them and get them back to you on Friday, and I'll probably scan them back to you, the results, and put them back in the basket. Any questions on anything? Okay, for what we're going to do on Wednesday, or what we're going to do next Monday, or how we're going to come up with the draft grades? If there's nothing, I believe that if you're a scholarship student, I believe that your stipends were finally processed by Hartford on Thursday afternoon. There's several of you that are meeting the scholarship standards. And I had a little money left over that I decided to reward you with some money. Those went out, close of business on Friday to Hartford. So hopefully those will be to you. Now, let's say they do them today, they'll be to you by Wednesday or Thursday of this week. Has anybody gotten their stipend yet that's a scholarship student? Okay. Well, everything's in the works. And then we'll start that process again with the January stipends. That'll be just for the scholarship students. Then I'll wait to see what, if anything, I have left over in May and try to help the others. There's any questions on anything. Again, I'll be around here today till probably 6 or 7, working on some projects for the dean and the president. Otherwise, I will see you Wednesday at 12:30. Okay, see you then.